Welcome back to the workshop. We want to continue taking a look at section 3.5, multivariate distributions. And now that we've discussed joint probability density functions, we want to take a look at the conditions for which a function may serve as a joint probability density function. Which are essentially the same conditions that we saw when we were looking at a probability density function, right? It still has to have a total area of 0, and it still has to be non-negative. So it's essentially the same thing that we've already taken a look at, but let's take a look at it anyway. Of course, things look a little bit different because we're looking at multiple variables. So a bivariate function can serve as a joint probability density function of a pair of continuous random variables, x and y, if its values satisfy two conditions. The first condition, again, is that it's non-negative, 0 or greater, for any value between negative infinity for x and any value between negative infinity and infinity for y, negative positive infinity, negative positive infinity. All right, and then of course, we need that total area beneath the graph of the function to be 1, because we're looking for probabilities here. We can't have probabilities greater than 1, so we need the total area beneath the graph to be 1. Excellent. So let's take a look at an example. We're saying in this case that this function can in fact serve as a probability density function, a joint probability density function, if we choose the right value of k. So in this case, what we would want to say, or what we would want to do, is we want to observe that all of the function's values are non-negative, but also find the value of k to make the integral equal to 1. Of course, we can say for k greater than or equal to 0, f of x comma y is greater than or equal to 0, because my x values and my y values are positive when I'm looking at this case. So positive times positive times positive is positive, and then it's 0 otherwise. So excellent, because I'm right between 0 and 1, but also satisfying that the sum is less than 1. So yes, everything looks good for positive. So condition 1 is satisfied. For k values greater than or equal to 0. So as long as we find a k value that does that, then we have a k value that's good to go, and this may serve as a joint probability density function. Let's see here, to satisfy the second condition, we need that the integral from negative infinity to positive infinity and from negative infinity to positive infinity of the function, integrate with respect to x, then y, we need that to be equal to 1. Again, we need that area to be 1. All right, excellent. So a couple different things to make note of here. The primary thing being integration bounds. What are we actually integrating over? Well, all that we need to integrate over is the non-zero region. So let's notice or observe what the non-zero region is. So give my axes here a moment again. I'm working from 0 to 1 and from 0 to 1. And I need positive values of x and y, where they are also, the sum is less than or equal to 1. So I need to have, let's see here, x plus y is less than 1. So what I do is I plot the line x equals y minus 1. Oh, let's see here. x equals y minus 1. That looks pretty good. So again, that line is x equals y minus 1. Now again, a lot of times what you would do is you would have it y equals, and actually it's not y minus 1, it's 1 minus y. There we go. A lot of times you would have it be y equals something because that's the way we typically do it. But with this integrating with respect to x first, it's most convenient to write this way. So what is the region that we're interested in? Well, we're interested in this triangular region. So it's very similar to the setup of our previous problem. So when I draw my rectangle, so that way I can understand my integration over x first, then I'd be integrating from 0 all the way up to this value here, and that value there is given by x equals y, 1 minus y. Okay, so that tells me my integration bounds for x, and then of course for y, now I can consider any value that y takes on, and that goes from 0 to 1. So the integral from negative infinity to positive infinity with respect to y, and the integral from negative infinity to positive infinity with respect to x of our function is actually equal to, right? When I talk about this integral, this is defined piecewise, so I have to split it up into the different regions where it's 0 or non-zero. But all the regions where it's 0 mean nothing to me because they're 0, so I'm just going to essentially drop them off right away. So my non-zero region is the integral from my y, which is second, goes from 0 to 1, 0 to 1, and the integral for x goes from 0 to 1 minus y. And the function that we have in this case is k times x times y. K times x times y, dx, dy. Now, I'd like to get some practice in with Mathematica, so I'm going to go ahead and open that document again. Let's see, find our way over to Mathematica. Here we are. And when we take a look at this, we want to integrate. And what are we integrating? We are integrating k times x times y. It is important to have the multiplication symbols there because you can give variables names. So it might think that you're talking about kxy, or when you tell it to integrate with respect to x, it won't see it because all it sees is kxy. It doesn't see k, x, and y. It just sees the one thing, kxy. So we have to write the multiplication in between. We integrate with respect to x first. So x, we're integrating from 0 all the way up to, we said 1 minus y. Excellent. And close that bracket. Shift enter. And that gives us what we're integrating now with respect to y. So that's 1/2 of k times 1 minus y squared times y. So what we have is we have that this is equal to the integral from 0 to 1 of, we said 1/2 k times 1 minus y squared times y dy. But of course, I don't want to work for that either. I'm just going to go ahead and plug that in. So this would be, no reason to type it all in again. Just again tell it to integrate the thing that you just integrated, but it is case sensitive. So make sure you get that right. And then we are integrating now with respect to y, and from 0 to 1. Excellent. So we get k over 24. So this is k over 24. But we need this integral to be equal to 1. So for k equal to 24, fxy is or can be, may serve as, it doesn't necessarily, we're not saying it is, it just can serve as one. So this function can serve as a joint probability, I'm sorry, joint, joint probability density, there we go, function. All right, excellent. And that's all that we wanted to take a look at for this video. In the next video, we'll take a look at the cumulative distribution, of course. That also looks very similar to what we saw in the previous sections. So I'll see you guys back in the workshop very shortly.